The story of the origin of our universe and its complex evolution is a story that spans billions of years and contains complex theories and amazing discoveries that challenge our understanding of time, space, and existence itself. The universe began approximately 13.75 billion years ago with an event commonly known as the Big Bang, a large explosion that created all matter and energy. But despite our advances in cosmology, the exact causes of this event remain a mystery. Scientists have determined that 380,000 years after the Big Bang, a major change occurred. The universe cooled enough for atoms to form and went from an opaque soup of electrically charged particles to a transparent state. This period, known as the recombination era, allowed light to travel freely, making the universe visible. Imagine that the universe is a giant, bright star in its early stages, too hot for electrons to orbit nuclei, preventing the formation of atoms. This prevented light from escaping, making the universe opaque. It is fascinating to think that before this period of change, the universe was a chaotic plasma of particles, illustrating the immense power and intensity of the initial conditions after the Big Bang. Now consider the idea that the universe may have existed before the Big Bang. This idea may seem wild at first, but it has been supported by prominent physicists, including Brian Cox. This perspective brings an interesting dimension to understanding cosmology, suggesting that what we traditionally define as a beginning may not be an absolute beginning. Brian Cox elaborates on this by referring to Einstein's theory that the Big Bang created the universe, a notion widely accepted in cosmology textbooks. However, recent insights suggest that the stage before the Big Bang is known as inflation. This phase was characterized by the exponential expansion of the universe with an astonishing speed, doubling several times within a fraction of a second. This rapid inflation smoothed out any initial irregularities and created the unified cosmos we observe today. When this period of inflation ended, the energy that drove it was released into space, heating it and creating the particles that formed the universe as we know it. The concept of inflation raises profound questions about the nature of the universe. What started this rapid expansion and what caused it to stop? How long did this phase last? Although scientists have not yet found definitive answers, several theories suggest that our universe may be one of many in a vast multiverse. This notion, although speculative, is scientifically plausible and the subject of active research. This suggests that the constants of nature, such as the force of gravity, the speed of light, and the masses of particles, can vary from universe to universe. This multiverse theory can explain why our universe seems so configured for life. Among countless universes with different characteristics, we live in the one that allows us to exist. Renowned physicist Roger Penrose offers a compelling extension of these ideas with his theory of conformal cyclic cosmology, CCC. Penrose, who boasts a Nobel Prize and a knighthood for his scientific achievements, suggests that our universe is just one in an endless cycle of universes, each born from the remnants of the previous one. This theory redefines our understanding of time and space by proposing multiple beginnings and ends rather than a single beginning and end. According to the CCC, when the universe reaches a perfect equilibrium without matter and measurable forces, a new universe emerges from that equilibrium, starting the cycle again. The James Webb Space Telescope has produced exciting data that supports some aspects of the CCC and challenge traditional cosmological models. The discovery of early galaxies and black holes that appeared to exist only hundreds of millions of years after the Big Bang raises questions about the normal timeline of cosmic evolution. For example, a mature galaxy similar to the Milky Way did not exist until 2 billion years after the Big Bang. This rapid galaxy formation indicates a more complex and accelerated process than previously thought, and is consistent with the CCC's proposal that elements of the previous universe are transferred to the new one. Penrose's CCC theory is complex, based on his theory of general relativity and quantum mechanics. He noted the importance of singularities and the cosmic microwave background, CMB, of the Big Bang. Penrose discovered that the universe probably began in a very low entropy state, as evidenced by the flat and ordered state of the CMB. Central to the CCC are Hawking points, small regions of the CMB that may be remnants of black holes from previous cycles. Those primordial black holes may have evaporated, leaving detectable traces in the CMB of the next universe. Next to these ideas is the theory of inflation, first proposed by physicists Alan Guth and Andre Linde in the 1980s. Inflation assumes that there was a brief but massive expansion right after the Big Bang that smoothed out all the irregularities and laid the foundation for the large-scale structure of the universe. This rapid inflation was driven by the form of thrust allowed by Einstein's general relativity. Although gravity is normally attractive, under certain conditions it can act repulsively and promote the rapid expansion of the universe. Constant inflation expands on this idea and suggests that the inflationary process never completely stops. Instead, it persists in some region of space, giving rise to a potentially infinite number of universes in the multiverse. Each universe in this multiverse can have different physical laws and constants, creating a vast landscape of cosmic diversity. This framework introduces the concept of a cyclical universe and emphasizes constant renewal and expansion rather than a single beginning and end. Multiverse theory. The concept of a cyclical universe resonates deeply. Just as the Earth experiences continuous life cycles and seasons, the universe experiences endless cycles of birth, death, and rebirth. This perspective aligns with the larger dimension of eternal inflation, presenting the multiverse as a sphere of eternal development and creation. The interaction of different universes, each with unique characteristics and timelines, challenges our conventional understanding of time and place. Neil deGrasse Tyson, a famous astrophysicist, adds another layer to this discussion. He speculates that the James Webb Space Telescope has detected evidence of black holes in the previous universe. If true, this discovery suggests that our universe is part of an endless series of cosmic births, necessitating a re-evaluation of the history of cosmology. Tyson emphasizes that we are not just part of the universe. The universe is also within us. This deep connection underscores the importance of understanding our place in the cosmos and our origins. The search for these answers is driven by humanity's fundamental curiosity about existence. Where did the universe begin? Was it a product of grand design or just a coincidence? These questions have
fascinated thinkers for centuries, from ancient philosophers to modern scientists. Although Einstein sought a unified field theory to explain how the universe works, that final equation remains elusive. Scientists continue to explore the mysteries of the cosmos in hopes of discovering the fundamental principles of our reality. As we delve deeper into the mysteries of the universe, we face new challenges and revelations. The behavior of subatomic particles and the vastness of space both provide clues and raise more questions. Observations from a telescope like the James Webb, which capture light that has traveled for billions of years, provide valuable insights, but also remind us of the limitations of our perspective. Despite these challenges, the quest for knowledge continues, driven by the belief that understanding the universe will illuminate the answers to our deepest questions. Black holes, for example, play a crucial role in this cosmic puzzle. Those enigmatic creatures, where gravity is so strong that even light cannot escape, are probably the primordial creatures of the universe. They significantly influence the formation and evolution of galaxies. Recent discoveries indicate that there were supermassive black holes near the Big Bang, supporting Penrose's CCC theory. This theory requires that black holes from a previous cycle of the universe can remain or leave detectable traces in the new universe. The interaction between black holes and the evolution of the universe is complex. As black holes consume matter, they affect the surrounding space and the formation and growth of galaxies. In Penrose's CCC, the final state of the universe, dominated by black holes, closely resembles the conditions at the start of a new cycle. This cyclicality challenges our understanding of time and suggests that it may be an endless loop rather than a linear progression. The concept of time itself is debated. In relativity, time and space are intertwined to form a four-dimensional continuum affected by mass and energy. This framework has shaped our understanding of the universe, but it does not necessarily encompass all aspects of reality. Some physicists suggest that time may be an emergent property resulting from the interaction of more fundamental entities. This idea is compatible with multiverse and cyclical universe theories, where the nature of time can vary in different universes and cycles. The search for a common theory that perfectly unites general relativity and quantum mechanics continues. These two pillars of modern physics describe different aspects of reality. General relativity explains the large-scale structure of the universe, while quantum mechanics governs the subatomic world. Finding a theory that reconciles these two frames of reference is one of the biggest challenges in physics. Such a theory, often called a theory of everything, would provide a comprehensive understanding of the origin, structure, and behavior of the universe. In exploring these deep questions, we must also consider the philosophical implications. The idea that our universe is one of many, each with different laws and constants, challenges traditional notions of uniqueness and purpose. It raises questions about our place in the cosmos and the nature of reality itself. If all possible universes exist, what does that mean for concepts like free will and fate? These questions bridge the gap between science and philosophy, emphasizing the importance of interdisciplinary research in understanding our existence. Considering these theories and discoveries, it is clear that our journey to understand the universe is not far off.